In this video, we're going to look at transforming functions that have already been transformed. And so transformations can be applied to any function, whether it is a basic function like an x squared function, or it's an x squared function that has already been transformed and is then going to be transformed again. So one of the common things that they ask you to do when transforming transformed functions is to undo transformations. So they might give you some transformed parabola and ask you the transformations that are required to get back to the basic x squared parabola. The other sort of question that you get is transforming functions to fit a specific requirement. So whether it's a specific equation that is not the basic equation for that, or whether it has a particular property over a specified domain, such as 1x-intercept over this domain, or whether it is a function with a restricted domain. We're going to have a look at all of those. So our generic transformation pattern for methods is y is equal to a f of n times x plus b plus c. And the green lettered transformations are transformations that affect y values, and the yellow ones are transformations that affect x values. So changes to our y coordinates. There's two things that the A does. It dilates, which means it stretches. Now the stretch is in this direction, which you can describe in the exam as vertical. You can describe it as parallel to the y-axis, or you can describe it as from the x-axis, but you must include the words by a factor of and then the number. It's not dilation 3, okay? It's dilation by a factor of 3. Don't write dilation 3, it's not correct, all right? You need to have the words by a factor of. The other thing it does is it does a reflection, and it reflects this way across the x-axis. Okay, it uses the x-axis as a mirror line. So use the words across the x-axis. For the translation at the end, there's all sorts of fancy ways of describing it. The translation is in this direction, and the simplest way are the words up and down. So if it's plus 3, it's up 3. If it's minus 3, it's down 3. Don't overcomplicate it. Use the words up and down. The changes for x value are a little bit more complicated. The n value, the same as the A, does dilation and reflection. This time the dilation is a horizontal dilation. So you can use equivalent words to here. So the y changes were vertical, so the x changes will be horizontal. Parallel to the y-axis is these will be parallel to the x-axis. From the x-axis, these will be from the y value. Whichever way you describe it, you have to get this direction correct. And you also need to, again, use by a factor of, and it's complicated because it's actually 1 on n. It's not times n. The reflection is reflecting in this way, so we're swapping this direction, which is across the y-axis. And our translations, you'll notice I've got plus b here in this bracket up here, and this allows me to say that my translation is negative b units. Okay, so it's the opposite to whatever is here. Sometimes you'll see that this is a minus in here, then that would mean it would be b units. But the b does translations left and right, super simple, not in 3 units in the positive direction of the x-axis or the negative direction of the x-axis. Left and right is fine, and it's negative b units. It's the opposite to whatever you've got in here. So if we have a function that's written in this particular format, we can read the transformations from left to right like we read a book in this direction, and that will take us from our original y equals f of x to the transformed function, just doing the transformations as they occur in this order from left to right. So if you like, we can write a transformation pathway if you think of it that way. So we start with f of x and we dilate it vertically by a factor of a, and we reflect it across the y-axis and we get to here. And then we dilate it by a factor of 1 on n and reflect it across the y-axis. I said y-axis before, I meant x-axis. And then we get this form of the function. And then we translate it horizontally and we get this form of the function. And then we move it up and down and we get this form of the function. So if they give us a function that's written in this format, and I've got a mistake in there, that should have brackets there. Then to get back to the original function, you should be able to see that all we need to do is to work back in the opposite order, and that'll get us back to our original function. So how does this work as an actual question itself? So let's do one and have a look. Okay, so what transformations are required to transform the graph of y is equal to 2 times 3x plus 5 all squared plus 4 to the graph of y equals x squared? So the transformed graph is in fact just an x squared graph originally that's been transformed. And when we have a look at it, it's not quite in the generic order that we need, because the coefficient of x is a 3 here. And we know from our generic pattern that it's supposed to be in brackets with just a 1 in front of it. So this 3 is going to need to come out of this whole thing as a common factor before we can work with it. So I've written the equation in the correct format and I've colour-coded our y changes to green and our x value changes, our x coordinate changes to yellow. And to bring the 3 out as a common factor from up here, you divide both of these things by 3. So divide the whole thing by 3, and that's where the 5 on 3 comes from. So now what I'm going to do is I'm going to start with my original x squared graph and I'm going to apply the transformation. So the first transformation that happened was it was dilated vertically by a factor of 2, and that gives me the 2x squared. So this is almost like the mapping. And then the next thing that happened was it was dilated horizontally by a factor of 1 on 3. So this gives me the 2 with the x with a 3 at the front, 3x. And then we moved it that direction, 5 on 3. And then finally, the last thing we did was we went up 4. And that gives us our final equation. I'll just leave that sitting off there. And so to get back to our original x squared after we've made all of these changes, we start at this end. And the very first thing we do is we undo up by 4. And to undo up by 4, we go down by 4. And so our first transformation is down 4. And that brings us to here. Then we come back this way. And so we're going to undo this left 5 on 3, which means that we're going to go that direction 5 on 3, which is right 5 on 3. Then we undo our horizontal translation. So again, it's going to be a horizontal translation, but this time it's going to be times by 3. So here it was times by a third. Here it's going to be times by a 3. So just move this in a little bit. Oh, come on. So what did I just say it was? It was dilation from y-axis by a factor of 3. And then finally we need to undo that times by 2. So we're going to times by half. So it's going to be dilation from x-axis by a factor of a half. And I've just gone the dits to make it quicker. And so you can see that whole working, backwards idea, undoing what was done. So this is a past exam question from 2015, and it's not a standard transformation question in that you're transforming a composite function. And so what you want to be thinking is, what changes do I need to make to the whole function? Do I need to multiply the whole function by something, or add something to the end of the whole function? Or are my changes actually within the function itself? So are my changes within what I've got in here? And that's what it is. So the changes that I'm going to need to make are going to be changes to my x value. So I'm going to need to either add something to the x, or I'm going to need to multiply the x by something when I replace it in here, so that that 8 disappears. And so what I'm going to need to do is to either multiply my x by something here, or add something here, so that it gets rid of this 8 here. So I'm not going to need to add anything, I don't think. All I need to do is to have x multiplied by something that when we cube the whole thing, so I get rid of that plus minus, plus b, get rid of that. So I'm just going to look for something multiplied by x that's going to give me something that will cancel with that 8 when I expand it out. And what I'm going to put in the n's place, I'm actually going to put a half in there. So what I'm going to get is y is equal to the square root of 8 times x on 2, or a half x cubed, plus 1, which is going to be the square root of 8 times by x cubed over 2 cubed, which is your 8. It's going to be the square root of 8 x cubed over 8 plus 1. The 8's will cancel, and I'll just get the square root of x cubed plus 1, which is what I need. And so the n that needs to go in, the value that needs to go in for n is in fact a half. And so what my equation becomes is the square root of 8 brackets a half x cubed plus 1. And in my transformed function, that is my n. A half is the n. And so what I have here is a dilation from the y-axis by a factor of 1 on n. And so my dilation factor is 1 over a half, which is 1 divided by a half. Oh, that's a half, which is 1 times 2 over 1, which is 2. And so, that should say 2. And so my answer is B. This question is also an exam question. So it gives you a sine function, a restricted sine function, and then tells you that the graph is transformed. And there's two transformations. First, a reflection in the x-axis, followed by a dilation of factor 4 from the y-axis. So the two transformations that we've got, I've written here. And so we're going to take our f of x function and we're going to make some changes to the function. We're going to make these two changes to the function. So a reflection in the x-axis changes the value of a to be minus 1. So we've got a is equal to minus 1. So the whole function is going to be multiplied by -1. The second transformation we've got here is a dilation of factor 4 from the y-axis. So this is a horizontal one. So this is our n value. And so our dilation for our n is it's horizontal times by a factor of 1 on n. And we know that our dilation factor is 4. So we've got that 1 on n is the same as times 4. So 1 on n is equal to 4. So 1 is equal to 4n. Our n value is equal to 1/4. And so what that means is for our function is that the whole of the function becomes negative. So it's going to be negative the whole lot of sine of 4x plus 1. It's going to be negative the whole lot of that function. And where the x is, we're going to replace it with 1/4 x. And so now our function becomes minus sine. 1/4 times 4 is 1, so that's just x. And then this plus 1 gets multiplied by the -1 to give us -1. So this is our equation that we're looking for. Now you'll notice that the answers themselves also have domains in them, and the domains are different. And so we need to, because we have changed our values for x, we did this dilation of a factor 4 from the y-axis. That changes the x values. This yellow bit here changes the x values. Our initial flip doesn't change the x values at all, so our domain would stay the same, but this definitely does. And so we need to do this dilation by a factor of 4 to our domain as well. Now, because we're working with our domain values are just a single x value for each of them, we apply the mapping transformations to do this. So we take our original x values, so dilation by a factor of 4 from the y-axis means that we take our x value and it gets replaced by 4x. This is our mapping pattern for a dilation by a factor of 4. Now, it's different in our formula because remember our formula is working with the final formula. We're working just straight with the individual value here, not every single x value or the formula. So what we're going to do is we're going to take each of those domain values and we're going to times them by 4. And so we get our new domain of 0 times 4 is 0, and pi on 2 times 4 gives you 4 pi on 2, which is 2 pi. And so that is our new domain. So putting our domain and our formula together, so our transformed domain and our transformed formula together, the correct answer is E.